Now, is it visible?
Yes, sir.
Okay. So yesterday
Sir.
we discussed about the 4D war. We completed 3D war and also we completed 4D war. We mentioned that in the 4D war, although we do try to consider the data which keeps coming continuously in time, and when the model forecast is made, then all those data which have already come during the integration of the model, that also can be utilized and assimilated in the model. That's the advantage of 4D war. But then many times the trajectory which the model forecast follows, the observations do not match with that trajectory. Now, there is one problem with the 4D war. The second problem with the 4D war is the computation of the adjoint of the model. People find that, especially for the nonlinear terms and the physical processes, especially which are more complex, like Akawas, word schemes, and so on. It is very difficult to compute the adjoint of the model. So 4D war was difficult to implement or was not able to provide as good result as we wanted. So then people started talking about the ensemble data assimilation, right? And we shall talk about that today. Now, what is the motivation behind the ensemble data assimilation? The ensemble forecasting that you have already discussed earlier is atmospheric predictability. The initial conditions and obtain a set of many initial conditions like 20, 30, 40 years, and respond each initial condition. Right? So, and also since we eventually try to take the ensemble mean of the forecast, right? So the ensemble mean is like a mean of the trajectories followed by different forecasts based upon different initial conditions. And so the ensemble forecasting provides for different forecast. In the initial condition of the model. So when we take the mean of the ensemble, provides the best estimate of the uncertainty of the forecast, right? And we can also, from the forecast trajectory, we can also calculate the probability of the occurrence of any event to that. So data assimilation requires information about the uncertainty in prior forecast and observations, right? Because whenever we are handling huge amount of data, we need to know what is the uncertainty in the data. And similarly, when we are making the forecast, we need to know what is the uncertainty in the forecast. And we say that the forecast, we are confident up to 95% level confidence or 99% level confidence we have, but still 1% uncertainty is there. So it is expected that if we know in prior that what is the uncertainty in the observation itself, right? In the first guess itself. So in the ensemble forecasting, we try to take care of those issues. More accurate estimate of uncertainty, less error in the analysis. Obviously, that's what we desired. In the data assimilation, we desire that our uncertainty should be estimated more accurately. Okay, and the analysis should have the least error. We would like to have improved initial conditions. Obviously, that is the main aim of the data assimilation, and improved ensemble forecasts. Once the initial conditions are improved, then the forecast also will be improved. The ensemble forecasting and data assimilation, of course, now that's what is the desirable thing. And this is an illustration, example of where the flow dependent first case errors help. Now let's see, these are the isotherms, let's say -5 degree, 0 degree, 5, 10, 15 degree isotherms. Okay, and this is a low here. What you see here is a front, right? A front. Do you remember the symbol of the front? You know the front, right? Front of systems. Yeah.
Yes, sir.
Yes. Yeah.
Yes, sir.
So this is a front. Okay. And let's say this is the first gauge. These contour lines or isotherms are obtained from the first gauge of this model 6-hour forecast. Okay. Now, let's say you have got some new observation. And the new observation, let us say, is here at this point. At this location, you have got a new observation. Right? So, now the fact that the contours are running like this, right? So, that means this side is low and this side is high, right? This side is high, this side is low. And here it shows a wind. Can you tell me what is the wind direction in terms of degree, approximately? From this wind bar, there is a wind bar here, plotted here. At this station, the wind observations are plotted. So by looking at the wind bar, can you tell me the wind direction? What is the wind direction here? Approximately. Tell me.
Northwest.
Huh? North? Tell
Northwest.
me. Yes, northwest. Because wind is coming from this. When you are drawing the bar, that means wind is coming like this. So wind is northwesterly. Correct? Right or no?
Yes,
Wind
sir.
is northwesterly. And what is the speed here? Denoted by this box.
15.
15. Yeah.
14.
Well, exact value is 14, but actually there is no way to represent one knot. So this is 14 knots. This is always represented in terms of the knots. When the wind is bars are drawn like this, wind speed is always denoted in terms of the knots. It is not in the meter per second. It is 10 plus 5, 15 knots, correct? So when you get an observation like this, and this is your first guess, then you would like to modify your first guess based upon the observation, right? Based upon the observation, you would like to modify your first guess. So let's see how, if you just use the 3D bar, how this first guess will be modified. The 3D bar produces an unappealing analysis, bowing the front out just in the region of the observation. When you are using the 3D bar, the way it does the analysis, you will see at this. Now, look at this. Now, by the 3D bar analysis, this front has been bulged like this. Okay, this is the new analysis produced by the 3D bar based upon this one observation at this location. This was your first case. This was the original position of the front, and this is the new position of the front. Let me use the laser pointer. Okay, so this is the original position of the front. This is the observation, and because of this new observation, the analysis made by the 3D bar system has produced or modified the front like this one. But this looks now a bit unusual because when you are doing the manual analysis, the curves should be more smoother than just sudden bulge in this curve. Because in old days, all the analysis used to be done by hand. Nowadays, everything is done by computer when there was no objective analysis system available. So people used to do analysis by hand. So a meteorologist or a handmade analysis would rather make it more smooth analysis rather than just a bulb. Okay. So when you use the 3D bar, this is how it looks like. But when you use the 4D bar or the ensemble data assimilation system, which produces more appropriate trajectories, looking at so many things, and then what you get is a better analysis. Now, the way an observation influences surrounding point is always the same in 3D bar. Typically, concentric rings of decreasing influence greater the distance from observations. Okay, I was telling you about the single pseudo observation test yesterday or day before yesterday, PSOT, pseudo single observation test, in the context of the background errors calculation. Now, I told you that when we do the background error calculation, then we would like to make a pseudo single observation test to see what is the influence of a single observation. Even if it is pseudo, some artificial observation, we try to inject into the analysis and make a single pseudo observation test. Okay. So this is the single pseudo observation test. All right. So if you do that, then this is how it will look like. Okay. And typically in the single pseudo observation test, it will make like concentric rings around the observation, decreasing influence greater the distance from the observations. Okay. Here is the front you would redraw based on synoptic situation, intuition, understanding that the errors are flow dependent. Okay. If you are doing a manual analysis, you would like to have a front more like this one, which is more smoother, and just shift it because of the new observation here. Okay. So this is how you would like to do. So in this special case, your synoptic intuition would tell you that temperature errors ought to be correlated along the front from northeast to southwest. Okay. However, you would not expect that the same northeast-southwest correlation if the observations were near the bomb front. Okay, depends on where the observations are. Analyses might be improved dramatically if the errors could have this flow dependency. Okay, if your errors, the observational errors and the analysis errors have the flow dependency, then it would be much improved. And that flow dependency is what is missing in the 3D bar or even in the 4D bar. How can we teach data assimilation algorithms to do this? Okay. So we do that, or we teach the data assimilation to do that using the ensemble-based data assimilation algorithms. Now it can use ensemble to model the statistics of the first case background errors. Better blending of observations and the first case. It will do the better blending of observations and the first case. Okay. Initial tests show that dramatically improved sets of objective analyses. These sets of objective analyses are exactly the sort of initial conditions we need to initialize ensemble forecasts. So that was the philosophy behind the ensemble forecasting. Now, I we mentioned that in the ensemble forecasting, we try to estimate the uncertainty in the observation a priori, right? And having the knowledge of the uncertainty, we try to minimize the error difference between the observation and the analysis. Okay. And one very important tool used for this is the so-called Kalman filter. Kalman filter is a very important tool of statistics and widely used in so many applications. You have studied Kalman filter earlier. Did you study Kalman filter earlier?
Yes, sir, in stats.
Okay.
Yes,
Okay.
sir.
Okay, great. So Kalman filter is a very important tool. Nowadays so many applications of Kalman filter is done in even the real life applications. For example, you must have now seen so many these uh, taxi services, right? Ola, Uber services, right? You must have used it. And when you suppose call a Ola or Uber taxi service, it will tell you the location of the driver, taxi driver nearby your place, right? And it will give you the location and its number, and then you call the driver and you tell your location, although you also get the information about your location. But do you know how is that calculated?
Yes,
And
sir.
it is not, yeah, it is not the nearest driver to you. It is not the nearest driver. It is optimized because there will be so many taxis around you, and you don't know that which one, because they take into account not only the distance but also take into account which driver has been lying idle for longer. So they apply the Kalman filter in the algorithm, the software which they use to find out the location of the driver closer to your location. They use the Kalman filter in that. Right? So that's just one example. There are many examples of application of Kalman filter in our real life situation. And so also we apply the Kalman filter in the predictive analysis in the data assimilation. Okay. So Kalman filtering is an algorithm that uses a series of measurements of observed time containing statistical noise and other accuracies and produces estimates of unknown variables that tend to be more accurate than those with a single input by using Bayesian inference. Studied Bayesian function and estimating a joint probability distribution over the variables for each time step. Resulted in Dr. Rudolph E. Kalman. Okay. The Kalman filter is over 50 years old, okay, but is still one of the most potent and common data ingestion algorithms used today. Okay. Kalman filter is one of the most celebrated and popular data fusion algorithms in the field of information processing. Not only in our data assimilation, but so many applications are there. The most famous early use of Kalman filter was in the Apollo navigation. Remember Apollo mission, the first mission to the moon, right? Apollo navigation computer that took Neil Armstrong to the moon and most importantly brought him back to Earth safely. So in that computer navigation of the first landing of the Apollo mission on the moon, when Neil Armstrong landed on the moon, the application of Kalman filter was used in that computer. Which came to the moon and brought him back safely. So you can just imagine how accurate this measure of the uncertainty it can do, right? Today, common filters are at work in every device, smartphone, tracking targets like aircraft, missiles, using radars, building sensors, and many applications. Okay. So many applications in common filter. And that's what we also try to use now. And some systems. Okay. We also have a called TKF, example transform system. So what is common filter and how what can we do? Common filter is optimum estimator, that is inverse factors of interest from create uncertain observations. It is recursive so that new results can be processed as they are. Optimal in what sense? If all noise is gone, the computer minimizes the needless error of these parameters. What if the noise is not possible? Given the mean and standard base of noise, the Kalman filter is the best linear estimator. Non-linear estimators may be better. Okay. So why you use the word filter? The process of finding the best estimate from noise data comes to filtering out the noise. Right? So in the filter out the noise from the data. And similar also the millions of observations. It could be just one source like satellite or one source like radar. Millions of points around the globe where the light is collected, right? And obviously there can be so filter or filtering to which filters the noise from there. However, it cannot do but also projects these patterns to the state estimate. Okay, everything is projection. Right? Not a absolute cleaning up in terms of the cleanup sense in that sense, but it's just the projection of the estimates onto the estimate, the estimated value. So from first principles, the Bayesian data estimation looks like this. Let's say xt is your unknown truth value of the model state. Okay, and psi t is a function of quality, and psi t minus is the observation, which is today's observation as well as all your previous observations, t minus 1, t minus 2, t minus 3, and so on. So these are observations, current as well as all the previous observations. Okay, and this is what you like to estimate post area. Okay, which is proportional to P at current time and P at the prior time, the previous time. This is the base rule. This is also called the base rule. So the data estimation terminology, Y's, all the Y's are denoting the observation vector, which could include radiation observation, the satellite observations, etc. All the XB value indicates the B indicates the background state, the first case. All the XA indicate the analysis state vector. All the H indicate the operator to convert model state observations. Okay. R is the observation error covariance matrix. PB is the background error covariance matrix. PA is the analysis error covariance matrix. So analysis error covariance matrix, background error covariance matrix, observation error covariance matrix, and is the operator. The observation is operator to convert the model state into the observation, or observation state into the model field. First case. Okay. This is the analysis, this is background, and this is the observation vector itself. Okay, containing all kinds of observation. And because even different types of observations are dependent on each other. Like yesterday I mentioned that temperature can influence your wind, right? And it can also influence your relative humidity, because relative humidity is relative to temperature, right? So cooler the temperature, higher the relative humidity. Warmer the temperature, lower can be the relative humidity. You know that, right? And from the basic principles of physics, atmospheric physics, right? And that's why in the winter season you get higher relative humidity because temperatures are so cold, you immediately reach saturation. So what we are trying to say is that the observations are dependent on each other, highly dependent on each other, both horizontally as well as vertically. Okay. So the Kalman filter equation looks like this. Now, when you use the assimilation technique using the Kalman filter equation, then again this JXT, you remember the JXT is your cost function which you are trying to minimize. All these terms are same old terms which you saw in the 3D bar equation as well as in the 4D bar equation. Right? XT minus XV transpose of that. Right? So this is the background. This is the current time analysis. P, background error covariance matrix, the inverse of that, and XT minus XB plus HX, the observation operator, Again, this is y is the observation field. Transpose of that r. Okay, inverse hxt minus y. After a lot of mathematical juggleries, manipulations, we end up with the Kalman filter equations, which looks like this. If you want to read in detail, then you can read this paper by Laurent, published in QJRMS, Quarterly Journal of Royal Meteorological Society, 1986. Now, in this expression, these are the indications, notations. XA is equal to XB, the analysis, current analysis of any variable X is equal to background field plus K times Y minus HXB, where K is defined by this expression. Okay, this is called the Kalman gain matrix. This is also called the Kalman gain matrix. It indicates how much to weight the observations related to the background and how to spread their influence to the other grid points. Okay. This PA, this is the covariance matrix, analysis covariance matrix, given by I minus KH PB. So this is the analysis error covariance. The Kalman filter indicates not only the most likely state, but also quantifies the uncertainty in the analysis state. And this is the background. This is the analysis, this is the background field. Given by this expression, how the background errors at the next assimilation time are estimated. This is what is indicated here, in which M is the tangent linear of the forecast model. Also, we say that this is the adjoint of the model. Tangent linear of the forecast model, or also called the adjoint of the model, assumed like this: xt plus 1 is equal to mxt plus nl, and this one xt plus 1 at a future time is equal to mx of the current time of the analysis. Okay. This is how the Kalman filter equation looks like in the ensemble data assimilation system. So, as you know, everything is numerical, and numerical things are always not perfect. No, there are always uncertainties, imperfections, errors are there always. So, what are the problems there in Kalman filters? Now, in Kalman filter, the covariance propagation step is very expensive. They still need tangent linear adjoint models for evolving covariances. Linear error growth assumption still is questionable. Right? During the time step, the assumption that the errors grow linearly is a questionable point. And they also need still the advanced models, which are again complex. So from Kalman filter, we go to the ensemble Kalman filter. So what if we estimate the PD at the background error covariance matrix from a random ensemble of forecast? Okay, it is given in this paper, Journal of Geophysical Research. Let's design a procedure so if error growth is linear and ensemble size is infinite, that means your large data set is very, very large, then it can give same result as the Kalman filter. So depends upon the size of your ensemble data. So the ensemble Kalman filter, also denoted as EMKF, is a recursive filter suitable for problems with a large number of variables. And that's what we have in atmospheric models, very large number of variables, such as discretizations of partial differential equations in geophysical models. It is now an important data estimation component of ensemble forecasting. The ensemble Kalman filter is related to particle filter ensemble member, but the ensemble Kalman filter makes the assumption that all probability distributions involved are Gaussian when it is applicable. It is much more efficient than the particle filter. Okay, so this is what the ensemble Kalman filter's properties are. So let's see how the ensemble Kalman filter equations look like. It looks like this one. X at any point I of the analysis is equal to background field plus K, the Kalman gain filter. Remember the last slide, times Yi. All the Yi's are the observations. This is the background. and this is the observation operator. H is the possibly the nonlinear operator from model to observation space. And this K is given by this one. Again, this indicates the background covariance matrix, observation operator, transpose of that. Okay. X is the state vector of the I is the ith member. PB, background covariance matrix, is equal to X times XT. Okay, but this capital X is defined as this one. Okay, transpose of that. So, in the ensemble Kalman filter equations, an ensemble of parallel data assimilation cycle is conducted, assimilating perturbed observations. So, earlier we were saying that we are trying to perturb the initial conditions to make the ensemble forecasting, but here we are also trying to perturb the observation because we do not know or you are not sure how accurate is your observation. Right? So you perturb the observation itself to measure the uncertainties in the observation. And secondly, the background error covariance are estimated using the ensemble. So these are the two important points of the ensemble Kalman filter equations. Okay, data assimilation. Now this is the schematic of a ensemble Kalman filter data assimilation system. So you have got different members. Member 1, forecast from member 1, forecast from member 2, forecast from member 3, and so on. So many members, as many forecasts. Okay. Then you have got a set of observations at a given time. Okay. So those observations you perturb. Okay. Put into the ensemble Kalman filter, and it will filter the noise from there, make the first member's analysis based upon the first member. Then again, the second part of observations, like that you have got so many observations, you put up the second observations, put in the ensemble Kalman filter the noise, produce the analysis based upon the second member, and so on. You go on. But within all the observations, at the depend upon how far you want to go from your point of interest. And like that, you have got a number of analysis, which indicate the number of initial conditions, and from there, from each of these initial conditions, again you make forecast. New forecast from number 1, new forecast from the number 2, new forecast from the number 3. Okay, and then you reach the next analysis time or observation time, and at that new observation time, you have got the new observations, right? So all these new observations, again, you repeat the same way, right? Again, you put up all the observations, each observations. Now, apply the Kalman filter, ensemble Kalman filter, get the new analysis for each of those observations, and then based upon that, you get the new analysis, and then make a new forecast, right? And then for each of the member, and it will go to the next cycle like that. So this is how is the flow diagram of a ensemble Kalman filter data assimilation system, right? Ensemble Kalman filter data assimilation system. So you have to just look at this flow diagram to understand the ensemble Kalman filter data assimilation in summary, right? You are trying to perturb each observation, filter out the noise using the ensemble Kalman filter, make the new analysis for that number, make the new forecast based upon that, and go on to the next cycle. So this entire schematic diagram is a representation of the ensemble Kalman filter data assimilation system. Okay, is that clear? Are you able to hear me? Am I audible? Hello? Hello?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Oh, I thought I'm disconnected. I thought. Okay. So fine, good. So this completes your data assimilation schemes. Okay, data assimilation system. And basically, it completes your course of NWP. This small tail is there, assimilation of Doppler method data. We can discuss this also, of course, no problem. But this is just application. how we assimilate the Doppler weather radar data. This is what just a kind of illustration or demonstration of data assimilation in assimilating the radar data. But why only radar data? No, URS. You have to assimilate even satellite data. You have to assimilate even the surface observations. You have to assimilate even the upper air observations. So many observations. But in the syllabus, this topic was there just for the sake of making you familiar with this Doppler weather data estimation. So I think we will try to complete this so that our syllabus will be over. Is 11:50 now. There is a seminar by Professor Rajesh Kumar at 12 o'clock. So I think we can finish before that. We'll try to finish it. So Doppler radar data processing. What do we do? As you know, we have discussed it earlier that the two most important things which are measured by Doppler radar are, tell me, one, what is the one?
Reflectivity and radial velocity.
Yeah, exactly. Reflectivity and the radial velocity. And there are many other byproducts also, of course. But the one which we try to assimilate in the model is the reflectivity and the Doppler velocity. Okay. So somehow we have to develop a so-called observation operator, right? We mentioned about the observation operator earlier in the class, that we have to have the observation operator which can map the observations space into the model background field, right? And especially for those observations which are not prognostic. And we know that neither the reflectivity nor the Doppler velocity is a prognostic coefficient. Right? We try to diagnose the reflectivity in the model based upon the cloud microphysics or the cloud microphysical parameters which are predicted by the model. So based upon those cloud microphysical parameters estimated by the model, we try to diagnose the reflectivity, because we know that the reflectivity depends on the hygrometeor contents of the clouds, right? And similarly, the Doppler velocity, actually it is a radial velocity, right? Because when you are measuring the, sending a pulse from a radar and it gets reflected back to your receiver, and your radar antenna is a disk antenna which is scanning the sky, both azimuthally, in the azimuth direction 360 degree, and in the vertical 0 to 90 elevation, right? So that is in the polar coordinate system. The information that you receive from the Doppler radar is in the polar coordinate system. Okay. So the velocity which you calculate from there is the Doppler velocity, which has to be again mapped into the Cartesian coordinate velocity, because you need eventually to know what is the zonal velocity and what is the meridional velocity, what is the u component and what is the v component. So you need to convert that radial velocity in terms of the Cartesian component velocity. Okay. So first we try to do these things, and these are the part of the radar data processing. Before we can assimilate the radar data, we try to process the data, radar data processing. There are several techniques and scientific challenges in the data assimilation. Okay. And see, as usual, any data, any new data, when you are trying to assimilate, first thing you should know is how much is the error in the data. Right? So in the DWR data processing also, DWR is the Doppler weather radar. Okay, the Doppler weather radar data processing, you have to first of all also estimate the error. One is of course the manufacturing error. The manufacturer of the radar will tell you that what is the manufacturing error. But there are many other uncertainties also. Now we have seen how to filter out the uncertainties using the Kalman filter or ensemble Kalman filtering. So the radar data processing, now is quite a challenging thing before you can assimilate the data. And there are several techniques used for that. Number one, normally the radar data is available at very high resolution because so many echoes are there, so many clouds are there. And you will receive echoes from all different targets, objects, which are the clouds. Okay, as compared to the analysis resolution. So a huge number of data. Thus, it is desirable to develop a suitable technique to thin the data to match with the analysis resolution. Okay. So, in other words, if your resolution of the model is coarse, then you won't get much benefit of the radar data assimilation because your data is very, very high density. Too many data you have got. So you will feel the advantage or benefit of the radar data assimilation only when your model resolution is final, like 1 kilometer, 2 kilometer, or 3 kilometer, let us say. But certainly less than 10 kilometer, your resolution you should have to feel the impact or benefit of the radar data assimilation. Mapping, interpolation, smoothing, super observation, data filling, these are all the data processing part. Okay, all these things have to be done, and you know all of them one by one we have discussed. Smoothing, super observations, like too many observations jumbled together, data filling, like where there are some gaps also sometimes that have to be filled up also. There can be gaps also in the radar data, right? Like, suppose if your radar is installed in a hilly region, in a mountainous region. Nowadays, IMD is installing many top radars in the Himalayas. Already, I think, Uttarakhand, they have placed 2 radars. One at, I think, Surkunda Devi probably, and then one more Bageshwar, and I think third radar somewhere. I mean, in each state of the northern states of Jammu, Kashmir, Himachal Pradesh, Uttarakhand, each state they are going to install 3 radars. Jammu and Kashmir already has 1 radar at Srinagar, and another one they have installed just recently. They are installing at Sonamarg. If you have heard about the Sonamarg, is a very good tourist place of interest, Sonamarg. So they have installed another radar at Sonamarg. So all those radars, the problem is that because there are so many mountains around that, so the radar pulses get reflected from the mountains. So there is a blocking by the mountains, and those blockings make data gap region, right? Data gap region. So even when we have a radar, we get the data gap region. So we need to fill up those data gap region, and all these things are part of the radar data processing. Number 2, quality control is very important before assimilation of radar data into the WRF VAR analysis. Quality control, okay, which includes to deal with the clutter, anomalous propagation, faulty velocity, and other noises. So noises. Sometimes you might have heard that there are swarms in the atmosphere, or a huge number of birds flying, and when the radar sends a signal pulse, the pulse gets reflected back from the birds. Have you heard of that? Yes or no?
Yes,
So
sir.
birds can reflect the pulses of the radar, and you get a noise, a pulse echo, as if there are clouds, and they are not clouds in reality. So they appear like a clutter. I mean, if you study the radar data processing, you have got a course. I think you have studied earlier, or I don't know, or in this semester. Radar
This
data.
semester.
Huh?
This
Next semester?
semester, meteorological applications.
Yeah, you have studied already, right? So I
Yes,
don't
sir.
know whether these things you have studied or not, whether these things were there in the syllabus, but they are part of the radar meteorology. Okay, radar meteorology is a separate subject in itself. So all these clutters, anomalous propagations, etc., have to be filtered out. Number 3, the error variance of the upload with the radar data needs to be determined and is specified in order to assimilate the radar data observations effectively, together with other sources of information. Okay. There is no standard software included in WRF to process the raw radar data. Although if you read the WRF data assimilation system, there is a provision. They have made provisions for estimating many types of data. Now, of course, the standard data like survey data, operator data, assimilation provision is there. Satellite data also is there. How to assimilate satellite data also is there in the WRF model, VAR. And recently, I think they have also got the module for assimilating the radar data. So you can assimilate the radar data in the WRF model, but how to quality control, how to process the radar data, that part is not there in the WRF model. I think it is not there. Now, at least they have not made it public. I mean, they must be doing themselves because when they assimilate the radar observation, they must have processed the data first before assimilating. But because they know that this data processing of the radar or quality control of the radar data is dependent upon the manufacturer of the radar. Maybe the US people are using some different radars, and India is using some different radars. So the quality control process may vary. So the quality control algorithm of the radar data is not there in the WRF model, at least not available for public. So that has to be developed by ourselves, and that's what IMD or NCM RWF actually has done. Has developed the quality control procedure for the radar data. Actually, they are still working on that. There is a team, there is a separate radar team at NCM RWF. Okay, now consisting of 3-4 scientists who work on this radar data processing at NCM RWF. Okay, IMD's job is only to collect the data, and then all the radar data is passed on to NCM RWF, where it is processed and quality control before it is assimilated in the model. So users should develop own pre-processor software and prepare a suitable input for WRF VAR, that is a variational assimilation. A software to prepare pre-process the Indian DWR data is developed at NCMRWF. It made range folding for radial velocity and reflectivity, and this part of the DWR data processing system. It processes the radar reflectivity from 10 to 60 decibel. dBz is the unit of the reflectivity echo. Okay. The radial velocity absolute value from 2 to 30 meters per second is the range it can process. I think probably already 12 o'clock. Try to quickly finish. A strategy is designed within the preprocessor software to thin the voluminous Indian DWR data set. Okay. It builds a desired thinning grid, two-dimensional. It collects maximum specified number of radar observations in each thinning grid square, and for each grid square, identify the nearest data location with maximum number of levels from left lower corner, okay, of the grid. After thinning, two sets of data are produced: one, input for WRF variational assimilation system, and two, data suitable for plotting the process data, radar data files through NCL graphics. The NCL is NCAR graphics command language. So, as I said, you have to have an observation operator. So, the observation operator for Doppler radial velocity is given by this equation. This is a radial velocity. You have the U component, B component, and W component. X minus xi, Ri. Okay, the Ri is the distance between the radar and the observation. Okay, and these are the coordinates. U, B, W are the wind components, Cartesian wind components. X, Y, Z are the radar locations. Okay, and Vt is the terminal velocity here. The terminal velocity Vt is calculated by this method, Sun and Crook, and estimated like this: Vt is equal to 5 is empirical constant, A times QR to the power 0.125, where QR is the rainwater mixing ratio. Okay. The observation operator for reflectivity is derived analytically by assuming the Marshall-Palmer distribution of raindrop size. The ZR relation between rainwater and reflectivity is given by this Sun and Group 1997 paper. This is the relation between the reflectivity and the rainfall. This is very important, importantly known as Zeta relationship. And people try to calculate their own Zeta relationship because it can differ from radar to radar. Generally, manufacturer of the radar does provide a Zeta relationship, but people try to verify that for their own location, or improve this or refine this Zeta relationship, because these constants can change, differ from radar to radar and place to place. Where Z is the reflectivity, is the unit of DVZ, and QR is the rainwater mixing ratio. When you calculate the increment variables for W and QR, okay, W prime and QR prime. So you have the control variables like psi prime, chi u prime, tu, p prime, surface, r prime, radial distance between the target and the radar or clouds in the radar. Okay, and you have got the model variables u, v, t, pq, standard model variables. So in the Doppler radar data assimilation, as you know now, we assimilate the radial velocity, in which we try to calculate the increments of the vertical velocity w prime to have a full assimilation of radial velocity data. Then reflectivity is the second thing which we try to assimilate in the model, in which the 3D water system needs at least one hydrometeor, that is the rainwater increments QR prime. So for radial velocity it requires W prime, and for reflectivity it requires QR prime. It is better to have increments of all hydrometeors variables such as snow, ice, etc. Well in advance in the 3D bar analysis system. But even if they are not available, at least with these two we can manage with. W prime and QR prime are obtained through diagnostic relationships. Okay. Then we calculate the increments of W in the bar to bar using the Richardson equation, okay, which is given by this expression. The Richardson equation is a high order approximation of the continuity equation than the incompressible continuity equation or inelastic continuity equation. It can build an efficient linkage between dynamic and thermodynamic fields because the thermodynamic equation is directly involved. Its computation is affordable, just a little more than the inelastic continuity equation. Okay, this is in some form a higher order approximation of the continuity equation. So, as you know, the hydrometeors are partitioned into different components, and there are different processes involved, like from QI, the specific humidity of the cloud, you get from the cloud a specific humidity, you get converted to the specific humidity at the location I. And these are different processes like rain processes. This is the condensation process, right? Some of them are conversion processes. How from rainwater to snow it can get converted, from ice to snow it can get converted, from cloud to ice it can get converted, back and forth. Where this is PCON is in condensation evaporation, PRA is accretion, PRC is the conversion, PID is the deposition, and so on. Okay, you can read the definitions or the symbols, meaning acronyms. Only the P condensation and PRA, the accretion, PRC, and PRE processes are included in the partition. Okay. Depends on how many types of hydrometeors you like to consider. So then you have the hydrometeor increments in the WR3D bar. A warm rain process is currently built in WR3D bar to bridge water hydrometeors and other variables. Okay. So from water vapor to cloud water, from water vapor to rainwater, so different processes, conversion process, okay, accretion process. These are the meaning of the acronyms. Okay. So this is just in a nutshell the philosophy behind the radar data assimilation. We try to process the radar data or decontrol the radar data, calculate the increments both for the vertical velocity, that is for the radial velocity conversion, and for the reflectivity through the rainwater, at least rainwater. And then these are the results, some of the results now of the impact of the data assimilation on simulating thunderstorms, which we tried to do long ago and published in different papers. This is the result published in Natural Hazards by Kiran et al. 2014. And these are the experiments which were conducted. Numerical experiments are conducted towards simulation of some thunderstorm case over Gangetic West Bengal. And the data of the Calcutta DWR was used, radial velocity from DWR Calcutta and reflectivity data were used to initialize the model initial condition at 00 and UTC using WRF Hart's data assimilation system. Two numerical experiments were carried out for this. One was the control, that is without assimilating the radar data, just making the forecast based upon FNL of NCEP analysis used as initial condition and boundary condition. And then second one in which you try to assimilate the data of DWR, reflectivity and the radial velocity, and try to see the impact. And this is what the impact of the radar data is in the forecast. So this is the actual observation of reflectivity from the Kolkata Doppler radar. Okay, this is the case of a square line system of 2009 May. Okay, there is a control experiment in which you do not assimilate the radar data. So you do see the evolution of the square line. Okay, by all these echoes, these are the reflectivity simulated by the model. Okay, but these are the reflectivity in which the DWR data has been assimilated. And you look at carefully, and you find that these are the square line. This is the square line. You try to match with the observation and calculate all the scores, skill scores of root mean square error, etc. You will notice that when you assimilate the DWR observations in the model, then your skill scores becomes better or errors reduces in the forecast. Okay, and so also the errors in the precipitation is reduced. Okay, so this is the observation. Observed precipitation, this is the time versus the rainfall, and this is the DWR, and this is the control. Red is the control in which you don't estimate the DWR data, and blue is the experiment in which you assimilate the DWR data. So you find that the blue line is more close to the black line, which is observation. So when you assimilate the radar data, your forecast of the rainfall is more close to the observation than compared to the control. This is what is the conclusion, and this was published in the Natural Hazards. So like that, we try to do many experiments and try to publish papers in other journals also. Okay, and so with this, we have completed your syllabus of NWP as a whole. Okay, including the data assimilation. All right, and shall stop for today. Tomorrow onwards, we shall discuss about the practical. And as I said, I'll try to take 3-4 classes about the WRF model also. Okay, besides the one, the exercises which you have been given already, those exercises you are supposed to do. We'll also try to discuss about the WRF model in the class. All right. So I think already 12:15. I have to stop because I want to attend his seminar. Okay, so I'm stopping this presentation. Okay, tomorrow we shall meet again.
Yes.
Okay,
sir.
sir.
I see only 9 people are there. Yeah, so okay, I stop the recording also. And they're going to Shivam. Shivam is there? So join later on the streams.